Okay, ich fange jetzt an. Glenn, bist du bereit?
No.
Okay, welcome everybody to our morning session, which consists of two talks today. It's Glenn Byrenheid, he will start the session, and afterwards Lutz Kämmerer. So Glenn, yeah, it's a pleasure to have him here in this session. So he was my former PhD student in Bonn, and he will talk about sparse approximation based on sampling, in brackets, information. Okay, please start. Stage is yours.
Okay, thank you for the opportunity to give a talk here. The things I will talk about today are topics contained in my PhD thesis, so everything should be understood as a joint work with Tino Ulrich. Let us start with a little motivating example. We consider the square root function, and we want to approximate this square root function by n equidistant knots. Looking like this, choosing these knots here. Then we easily can compute that we achieve an error of 1/4 square root n. Knowing something about the regularity of the square root function, so it's a half Hölder continuous. People with background in univariate approximation theory know we cannot achieve anything better than this bound. Approximation by equidistant knots can be interpreted as approximation from a linear subspace. If we allow more freedom, so-called free knot interpolation. So now we are allowed to place n free knots to interpolate our function. So we choose them such that the variation of our square root function is split into equal parts. Then we get an approximant U2, having the property with that he approximates the function f in the infinity norm by a rate 1/2n. Now we have to interpret this. I mean, these knots here are chosen dependent on our function f. This can be interpreted as an approximation by a nonlinear subspace. And as we see here, we have a better rate. So later we will come back to this example. Today we will speak about approximation using Faber-Schauder system. So our basic ingredient will be the Faber-Schauder basis. Faber proved in 1908 that every univariate continuous function can be decomposed as a series of head functions. So here or as dilated and translated head functions. Here we have first translate of level J1, second translate, and so on. Here level J equals 2. And the interesting point is that the coefficients in front of these head functions are function evaluations. So F0, F1, djk. So on the next slide, we see a little bit more explanation about these function evaluations. Namely, these are function evaluations in the first level. The first level is only to secure boundary values in the interval 0, 1, and every levels being bigger than j, being bigger than -1, they are based on the corresponding coefficients are based on second order differences centered around points k to the power k times 2 to the power -j. So again, j is the order of dilation of the head function, and k is the order of translation. So dilations and translations in the wavelet sense, for example. In this talk, we don't want to deal with the univariate case. We want to deal with the multivariate case. For that purpose, we simply tensorize in the wavelet sense the system of univariate head functions. Tensorizing in the wavelet sense means that we tensorize different levels. So it could be that we have to the first direction level 1 and to the second direction level 2, and both head functions are multiplied with each other in this construction. For this construction, one can easily show that the result of Faber from 1908 extends to the D-variate case. So every function f belonging to the class of d-dimensional continuous function can be expanded by such a series with convergence in L infinity. So in this case, with conditional convergence. For notation, we introduce here this dj. dj is the set of translates of the head function. So translates that cover our 0 interval, 0, 1. And the set of translates has for every fixed level j cardinality 2 to the 1 norm of the level. So now we have some system, and now we need functions we want to approximate. For that purpose, or better say, in this talk, we look on function spaces with mixed smoothness properties. Our functions are multivariate functions. Let me first introduce the spaces for RD. So we have functions mapping from RD into the complex numbers. We have several parameters. R always describes the smoothness parameter, P the so-called integrability parameter, and having R being some integer, the Sobolev space WRP in the two-dimensional case, for here in this case, is simply the set of all functions f belonging to LP, where this norm here is finite. That means we have the R's norm, or we have the R's weak derivative bounded in LP, and additionally we have such a term where we differentiate R times to every single direction simultaneously bounded in LP. And from this last term, the name comes from mixed norm or mixed smoothness, dominating mixed smoothness. A second class, which will be important in this talk, is the Besov class. The Besov class, there we have additionally some fine index, and the definition is now not by derivatives or weak derivatives, it's by differences. So in literature, they are sometimes called spaces with bounded mixed differences. So here we have some modulus of continuity. And this modulus of continuity, the first one acts to the first direction, this one acts to the second direction, and this one acts to the first and the second direction simultaneously. And for that reason, it's also a space with so-called dominating mixed smoothness. The fine index here, this says how to sum up this modulus of continuities with some weight in front, giving us the smoothness. So let us continue. Important in this talk will be, we deal with the question of sampling. For sampling, we need function evaluation. And this is given in case of R being bigger than 1 over P. So this is the Sobolev embedding theorem for spaces with mixed smoothness. Classical isotropic spaces, we have some dimension dependence. In this case of mixed smoothness, there is no dimension dependence in the Sobolev embedding theorem. That means we need simply R being bigger than 1 over P. And as a consequence, we find in every equivalence class in the space a continuous representation. So let us start to connect our Faber-Schauder system with the spaces of mixed smoothness. We have P between 1 and infinity. We have R being bigger than this embedding in continuous function and a maximum of a half. Additionally, R should be smaller than 1 plus the minimum over 1 over p and a half. Then every function f belonging to the Sobolev space can be represented by a series or by the Faber-Schauder series. The series converges unconditionally in the norm of the space itself. And the interesting point is that we can represent an equivalent norm of our function f by the decreasing properties of the corresponding Faber-Schauder head functions. That means we obtain an equivalent norm by measuring this sequence of Faber-Schauder coefficients inside of such a sequence space. That means for every fixed x, we square sum over all levels j with this rate our Faber-Schauder coefficients, and finally we integrate over all x. So this characteristic function here gives us a partition of the zero interval with this definition here. Okay. Let me connect this to classical Littlewood-Paley theory. For that, we do an unconventional comparison to the periodic setting, because to explain the non-periodic one would take more time. So, Littlewood-Paley theory. We have some functions where belonging to LP where Fourier transform is well defined. Then we decompose the Fourier plane, in this case here the picture of the two-dimensional one, into dyadic blocks. So this is the union of this are the blocks with level k being 4, 3. So k is a vector, and so on. So, and what we do is we sum up all Fourier coefficients with, or better say, we truncate the Fourier series to these blocks and call it delta k of f. Having such a decomposition of the Fourier plane, the Littlewood-Paley theorem says that if p is between 1 and infinity, we get an equivalent norm for our function f in LP by square summing these blocks and integrating them in LP. So we can use this method even to describe smoothness. Then we put an additional weight in front of these blocks. Here we see that this norm is very similar to our Faber-Schauder discretized norm. Here we had this cutout of the Fourier plane inside, and in our case of Faber-Schauder, we simply replace this by this sum of the Faber-Schauder coefficients of the corresponding level. So there are analog results for Besov spaces. In case of Besov spaces, the sequence space looks a little bit different. There we don't have to integrate. We simply have a double sum. And here's again this parameter theta, this fine index. Okay, so what I want to say is, with the help of the Faber-Schauder series, we can decompose functions f belonging to Sobolev or Besov space within a certain regularity area into, or we have saved every information of this in the Faber-Schauder coefficients, in this picture of Faber-Schauder coefficients. So here we have dilation levels, and the length of each, so every kernel length describes how many translates we have in what level. And inside of such norms, we have the effect that blocks with similar one norms in the level are equally weighted. So now we want to apply this Faber-Schauder characterizations for the problem of sampling recovery. We have seen this definition several times before, for example, in the talk of Volodya Temnyakov. So we define the linear sampling numbers as the best worst case error of approximating f by some linear algorithm using m function values of the function itself. So this is the benchmark for every linear sampling algorithm. And what we want to do now is we want to construct sampling operators by truncation of the Faber-Schauder series. Namely, we do the following truncation of the Faber-Schauder series, IMF, where we cut off all levels, or we simply want to approximate a function f only by the levels which have a one norm smaller than m. Remember, this dj was always a finite set. We had that these coefficients djk were generated only by function evaluations. So for every fixed m, this is some operator or some expression using only a finite number of function evaluations of f. This construction here yields a so-called Smoljak type sparse grid sampling operator. That means for fixed m, if we look on the points which are used to approximate our function, these are points from such a sparse grid here. And this truncation here in the picture where the length describes the number of translates ends up in such a quarter of a hyperbolic cross. So this is kind of hyperbolic cross approximation, I want to say. Now, what is the interesting point on such a truncation together with our Faber-Schauder representation? The point is that we can very easily express remainder terms, error terms for approximation errors. So if we consider the difference of f by f applied to, or the operator im applied to f, which was the sampling operator, then this can be simply expressed by such an expression where we have to sum up all levels. Here this should be one norm bigger than m. Then finally, this equivalent norm relations I presented before, they allow us to control this inside of norms in several function spaces. And this allows us very easily to reproduce a lot of results known for sampling recovery of of Sobolev and Besov spaces. This concept of sampling representations, this was originally introduced by Ding Dong for Besov spaces. So, for example, we can reproduce with such a method very easily in this for the non-periodic case the result from Temnyakov of 1993. So let p being between 1 and infinity, r being bigger than 1 over p and smaller than 1 plus 1 over p. Then we can bound the m's linear sampling number, where we measure the error in L infinity, and function comes from the Sobolev space from above by the supremum of all f belonging to the unit ball by the approximation of this given, sorry, here Sm should be Im. So this is the truncation operator I presented before. And this here equals up to asymptotically constants this rate. So here we see the effect that if we have several different integrabilities between source and target space, we pay some price in the rate. So we have to subtract from the smoothness the integrability of our model space. So multiplied with some logarithm. And this m here is chosen with this relation to the number of function values we want to use. Additionally, we could complete the picture for LQ, measuring error in LQ. So if we have P being smaller than Q, means we have in the model space where our function to approximate comes from, we have less integrability as in the target space where we measure our error, and we have R being bigger than 1 over P and smaller than 2 plus this. Then we can bound the M's linear sampling number from above again by the worst case approximation with our algorithm, and this coincides with this rate here. So we have m to the power -1 log d and to this exponential, or to this power, exactly. Now let us have a look on optimality of these rates. For sampling approximation, a benchmark result is given by linear widths. Linear widths simply describe the best worst case approximations of f belonging to the unit ball of our Sobolev space in this case by rank m operators, by linear operators having rank m. So then the following picture is known. I will mention some names later who proved important cases here. So we have this. If we compare this to our picture we achieved by this truncation operator, then we have that the sampling widths coincide. Okay, I should explain before. On this axis here, here we have the integrability of the space where we measure our error in the reciprocal version of it. Here we have the integrability of our model space where the functions we want to approximate come from. And then we have that this bounds we obtained coincide with, so are optimal coincide with the linear width in case that P is, so P smaller Q smaller 2, this is this case, and 2 is smaller P smaller Q, which is this case. In this corner here, this is the corner where the integrability of the model space is left of 2 and the integrability of the target space is right of 2. There we can prove that sampling approximation is seriously worse compared to linear approximation. So here we have that approximation by sampling is the same as approximation by general linear information. Here too, and here upstairs, this triangle, this is the case where the integrability in the source space is bigger than the integrability in the target space. So in this region, there was this recent progress due to Mario Ulrich, Tino Ulrich, Volodya Temlyakov, with this probabilistic methods. We already have seen some talks. Okay. Let me, here you find names connected with this estimates on linear widths. And let me continue. This linear sampling approximation was the first application for our Faber-Schauder discretizations. A second application is the consideration of sparse Faber-Schauder approximation, so sparse approximation. Sparse approximation we consider a set called dictionary containing all delates and translates of our system of Faber-Schauder head functions contained in this interval 0, 1. And what we are interested in is this quantity here, sigma m. Sigma m describes the best worst-case approximation of functions f by linear combinations of functions, or by linear combinations consisting out of m functions from our dictionary of Faber-Schauder head functions. And in our case, we will measure always in L infinity. So the interesting point is that every finite linear combination from the Faber-Schauder dictionary has the property that it's piecewise linear in every single coordinate direction. So this discretization theorems from above, where we had some equivalent norm between we have a function in Sobolev space of dominating mixed smoothness, and we can equivalently describe this by some sequence space of the Faber-Schauder coefficients. This allows us to discretize the problem of best n-time approximation in the function spaces to a problem of best n-time approximation in sequence spaces. And this sequence spaces, or this dictionary ED here, this is simply unit vectors in sequence spaces. So we have a discretization, and now afterwards, or better say, this widths here on the right-hand side, they were very well studied by Hansen and Zickel in 2010, 2011, 2012. And combining their result with the Faber-Schauder discretization theorem, this gives us the following weight. The following rate for the best n-time approximation of approximating Sobolev space with mixed smoothness in L infinity by Faber-Schauder dictionary. So here we have on a main rate m to the power minus r multiplied with some logarithmic term. And we can even bound the whole thing from below by m to the minus r. So we don't know anything about the sharpness of the logarithm here at the moment. Let us compare, or let me first explain what is the method behind that is realizing such a rate. The method is the following. Again, we look into the picture of this. So these blocks of djk, so the blocks containing the Faber-Schauder coefficients. And here we split these blocks into so-called hyperbolic layers. So in all layers which have the same L1 norm, having this, we spanned to every of this block a prescribed number of degrees of freedom, so of elements in our linear combination. And then inside of each block, one is doing a greedy strategy, namely taking the biggest coefficients. And finally, this will give us a set AM such that we find an approximate GM based on a linear combination of size m of Faber-Schauder head functions that achieves the rate on the last slide. The interesting point is that for the selection procedure, we don't have to know the full scope of Faber-Schauder coefficients. For any prescribed error, we have to know only a finite number of levels of this Faber-Schauder coefficients. And afterwards, so there we have to know them, and afterwards we select from this finite levels m coefficients or m head functions to build our approximant. So this means doing, or I should say something first, remembering that each djk here, which was the Faber-Schauder coefficients, was generated by function evaluations. This means we need to know a picture of function values. Afterwards, we pick some out of them, and this will give us our approximate. For that reason, this strategy I explain here can be considered as an adaptive sampling algorithm, but an adaptive sampling algorithm in some sense for compression issues. So the point is that we need more information than to generate our approximate than we use in the approximate finally. So for that reason, this M-time approximation gives us in some sense a benchmark quantity for compression problems. So now let us compare this sparse approximation results to results obtained for this linear sampling recovery before. Here we see that so again, integrability target space, integrability source space, and so on both pictures. Then we see that this best M-time approximation, it does not care about the difference in integrability. We have always main weight R, whereas we have in the case of linear sampling recovery, always, or the best we can improve at least, is always dependent on the integrability. And if you forget a log, at least in the main rate, this is sharp. So, meaning here nonlinear approximation benefits from having different integrabilities between source and target space. For that purpose, or for that reason, if we look back to our motivation example, for this square root function, one can prove that the corresponding Faber-Schauder coefficients are decreasing with this speed. This gives us that in case P being bigger than 2/3, that this sequence of Faber-Schauder head functions belongs to some kind of Besov type sequence space, defined like this. So this is a Besov type sequence space with B infinity. And from a generalization of this approximation theory, we obtain the result that we find an approximate Gn interpolating our function f in n points, having additionally the property that it's piecewise linear in every single direction. So having fixed d minus 1 directions and look only to 1, then you have a piecewise linear approximant, and that fulfills a rate of 1/n to the power 2, where n is in the end the number of interpolation nodes. So we can explain this rate by our theory, but the point is, reading carefully the book Constructive Approximation, one finds an example due to Rice in '69, who already had observed this effect before. Okay, let me quickly explain you an interesting case in connection with this sparse approximation. This is the so-called case of small smoothness. For that purpose, we consider Besov spaces with small fine index. In our case, fine index between 0 and 1. And we want to measure our error in space LQ. Interesting is the case where 1/p minus 1, where R is between 1/p minus 1/q and 1/theta minus 1. The explanation why this is really interesting, this goes back to the question, what are the corresponding sequence spaces we consider for giving bounds on n-time approximation. So I have not enough time to explain this in detail now. The point is that if we have here a little bit more smoothness even coming from our discretization theorems in Littlewood-Paley for Faber-Schauder series expansion of B spaces, then we get in such regularity areas rates for best n-time approximation by the Faber-Schauder dictionary measuring the error in L infinity, which have no additional logarithmic term. So they have only m to the power minus r and no additionally logarithm. And the interesting point is, in case of the Faber-Schauder dictionary, this result is even sharp. So we can construct a lower bound matching this. So, and for my knowledge, this should be one of the first sharp results dealing with n-time approximation in spaces with mixed smoothness having target space L infinity. So let me mention some further things quickly. So here we were, in this talk, we were always restricted to regularity up to 2 plus a little bit. These results can be generalized by, or were generalized by works of Dinsung and Derevianko-Ulrich. They used piecewise polynomial constructions, B-splines, and things closely related. Then you have similar properties with function that coefficients are generated by function evaluations and so on. So you can do the theory for higher regularity. And additionally, I want to mention that the things I have explained with this Faber-Schauder characterizations, there is also a periodic counterpart. Namely, we can replace our building blocks where we summed up our translates of the Faber-Schauder coefficients with this characteristic function by the dyadic tensorized differences of, for example, Delavallee-Poisson based sampling operators. And then one can obtain for the periodic setting also such a characterization of norms, where on the left-hand side here, this is generated by function evaluations. And I forgot to say, due to the similarity to this Littlewood-Paley type definition, we denote this or such an equivalent norm sometimes as discrete Littlewood-Paley type characterization. Thank you for your attention.
Yeah, thank you very much, Glenn, for your talk. Are there questions or comments? Maybe I have one. So I see here Sergei Konyagin in the list of attendees, and actually he did also work in this hyperbolic wavelet approximation together with Temlyakov and Devore. Mm-hmm. This is also connected to that, where they used projections to the wavelet hyperbolic cross space. That was in the 90s, 98, I guess. So in that sense, it is related to this work. So, and another thing, this small smoothness effect. So you explained it in terms of the sequence spaces, and so that there are now also new results for the sequence space for these iterated sequence spaces, if you want to approximate them in the sense of this Stechkin inequality, right? Mm-hmm. So this is the tool in this theorem.
Exactly.
Yeah, and just as a comment, so this can also be used for entropy numbers. So there are also similar results for entropy numbers. and even Gelfand numbers in this direction. And then, yeah, so this effect is kind of broader.
So what you want to say is you have such small smoothness effects with several S numbers or N widths or however.
Exactly, exactly.
Yes.
Yeah, and also there is a recent work with Volodya, together with Volodya, where we also computed Kolmogorov numbers in such a regime, but it's a bit different to what you did. Okay, further comments? This does not seem to be the case. So yeah, thank you, Glenn, for your interesting talk once again. And our next speaker will be Lutz Kämmerer, but I think we still have 5 minutes break.